Thank you, Jonathan, for your warm welcome and our mutual introductions. Really, from the somewhat facetious title, our presentation has the theme of measurement running right through it. But when you invited us to speak, really you were asking, how did an engineer and a surgeon get together? So we've included a little bit of that in our presentation this afternoon. And to make reference to one of this morning's presentations, there are no equations in our presentation this afternoon. There is some arithmetic, but that's being presented by the surgeon rather than the engineer. If we go back something over 100 years, the early 1920s, an engineer by the name of Alexander Pringle worked for James Mackey's and Sons. He'd been to Canada on a study tour to learn about Canadian manufacturing and met his wife, Grace, who we see in this picture. So he was, for the time, quite an entrepreneurial engineer. At about the same time, Surgeon Kirk, and it was not Mr. Kirk, he was titled Surgeon Kirk in those days, was approached by the Duchess of Abercorn to try and solve the problem of ex-servicemen who had suffered the loss of upper limbs in the First World War. Surgeon Kirk was certainly a character. He lived on University Square, in fact in one of these terraced houses that I think now incorporates Queen's Film Theatre. He operated in the Royal Victoria Hospital, failed his FRCS, but that wasn't actually necessary for him to practice in those days, and he refused to resit such an ill-considered examination. He commuted to the Royal Victoria Hospital in what was described as a gasoline cart, but apparently awoke most of South Belfast when it was en route. And he also set up a tablet making machine in the front room of this house for some sort of patent medicine that he had embraced, and apparently just about the whole terrace knew when the machine was running, so not a quiet character by any stretch of the imagination. What they developed was, at that time, an innovative artificial arm incorporating a hand which had a functional spring mechanism that could grip utensils and even tools, which led to re-employment of amputees. And this patent for that hand, you can see on the right, is signed by Alexander. Signed by Alexander Pringle. So that kind of personalises this relationship. About that time, or about 50 years later, I had just started in engineering, again in a traditional Belfast company in Harland and Wolff. No computer-aided design in those days, all ink and pencils. And as Jonathan mentioned in my introduction, I foresaw a career in mechanical engineering, in heavy engineering, in marine diesel engines. But at that point, another surgeon appeared on the scene and asked if I would go along and have a chat with him. I couldn't understand why a surgeon would possibly want an engineer. I understand now, of course. In fact, I understood after a couple of hours of speaking to Mr. James, Mr. William Victor James, to give him his forenames, known as Jimmy, but only to his friends. And I count myself as privileged to have known him as Jimmy James in those days. We ultimately got one of the Pringle and Kirk arms donated to us, and we're both really quite interested in that history. And it kind of brought us together. We had a constant dialogue, each trying to use each other's terminology, me medical terminology, of course, and him engineering terminology. And that's kind of how we learnt to communicate with each other and to participate in each other's fields. My early work was looking at photoelastic stress analysis, a technique which is really confined to history now. It involved making transparent plastic models, loading them and looking at fringe patterns from which you could determine both the magnitude and the directions of stresses. In this case, I was repeating an experiment published in the 1950s on a human hip joint. But then that's a small step to move to looking at objects that we can control the stresses in this case artificial hip joints. One of the first models I made, again The model gives rather a vivid image of stresses. And this was relevant at that time in the early 1980s because hip stems were still fracturing due to fatigue failure. So that brought me into the realms of orthopaedic engineering and bioengineering. But I became aware that in Musgrave Park, the Queen's University Department of Orthopaedic Surgery was based there, and there was an active group of registrars, surgical registrars, and scientists and mathematicians, all conducting research there. And that's really where I first met David. The pair of us were running around the hospital corridors in jeans and t-shirts, and both, importantly, conducting experimental research.
Thank you, John. Afternoon, everybody. Yes, so I started in the research department in August '84. I qualified in July '78, and I started orthopaedics in '83. And as John said, this was ongoing work, and that's an accelerometer that you see there. And they've been looking at noises produced from the knee. And this was probably 4 or 5 years old at that time, John, and several theses are already published. And these vibrations were caused by something inside the knee, so the kneecap moving over bits in the knee. So it came from within the knee surface. But on day one, on the 1st of August 1984, there were 3 channels in this machine. I decided to put on 3 accelerometers, and I found that the top and bottom actually were different signals, and it was silent in the middle. So I suddenly thought, this isn't coming from within the joint. This is actually rigid body movement of the patella, and the excitement was unbelievable. And this diagram went into my thesis. Now, how many of you here did a thesis where your first day's work went into your final thesis? So I was hooked. and of course it was, as John said, it was all about being able to measure. So the patella appeared to act like a seesaw, and I wanted to investigate rigid body motion. So I'll just let John expand a little bit on this bit.
Well, this was a perhaps rather unscientific experiment, but we were interested in David was making measurements through the soft tissues overlying the knee and the patella, and we were a little bit concerned about attenuation or perhaps some modification of the signal through measuring through soft tissue. For some reason, we decided to attach an accelerometer to a china cup, and we then discovered that by setting the china cup on different substrates, we were getting different results. The natural frequency of the vessel itself was being confounded by, again, whole body movement. So midway through the afternoon, we decided really we should standardize this, and we should be bonding the cup to an infinite mass. And the biggest thing we could think of as an infinite mass was the Earth itself. So we bonded it to the solid floor in the research department, and got some wonderfully clear signals. The next signal that arrived was Miss McCulloch, who was the senior orthopaedic nursing tutor, a delightful woman who aspired to retire to Dundalk, her hometown, and open a sweet shop. I don't know if she achieved that, but I certainly remember the afternoon when she looked at the setup and one of her best entertaining cups now bonded with super glue to the floor, and she uttered the phrase, "I am very disappointed in you, Mr. Beverland." She may have said something after that, but I'm not sure, because I had escaped by the door and left David to it. So that was the china cup model. As David described, the function of the kneecap was acting with ligaments on either side of the joint, and the patella, the bone which guides those ligaments over the front of the knee, was acting in this seesaw fashion, and that's what David wanted to analyse for his MD research.
And it was a floor polisher, I remember, John, too. This was the.
This was, well, yes.
Again, caused some consternation.
Sorry, go back one, but this was the floor polisher model, yes. What I've shown you is an anatomical diagram, and the one that went into David's thesis. In fact, the original apparatus was the departmental floor polisher upside down. So you've got the wheel here in the centre, and this was a ruler and some bits of string. Simple model. A lot was derived from such basic apparatus. And then, what were we doing with this, David?
Well, this was a model.
It's my milling cutter, but
you've forgotten it. You built this with me.
Oh, right. Well,
this was even more sophisticated, as you can see.
Yes. Well, the accelerometer is mounted on the top, and this produced was to replicate the slipstick motion. I don't remember a great deal about that particular model, but I do remember. Oh, right. This is the model from that.
Yeah.
Right.
Yeah.
Okay. So we're getting close to replicating what was happening in the patella. Now, this is a serious bit, folks, which I would probably be better nobody repeated this outside the room. We decided that the soft tissue problem was still an issue, and that really to benchmark the whole thing, we needed rigid coupling between the accelerometer and the patella. And this piece of apparatus was constructed. It comprises a sort of tower that the accelerometer could be pressed into, the recognisable connection clip from a battery, and this important component here, which fits in there, and this is the tip of a hypodermic needle. So the idea was that the part with the hypodermic needle here would be pressed into David's kneecap, and then that would give us, just for once off, to benchmark the measurements, it would give us a rigid coupling between his patella and the accelerometers. Did it work?
No.
Was it uncomfortable?
It was very painful. Yeah. And this thing here was like an aerial. It was swinging in the breeze. It was just total disaster.
Disaster. I didn't want to use that word. Disaster was the word. So we decided something more sophisticated was required, and the principle of the next iteration was to have molded plastic sort of drill guide mounted template on the surface. Here's the patella bone here lying in between its ligaments. We've got soft tissue in this gap, and here we've got the this molded perspex, which was made from a plaster cast from the volunteer's knee. And the volunteer was neither of us two. So the volunteer was either very courageous or he hadn't heard about the previous experiment. So we got this this molded, and here's the actual moulding, and by now it's got two aluminium drill guides fixed onto it, which were aligned with reference to X-rays. So that we're fairly sure when David put these wires down through, that when they penetrated through, they would actually meet the patella. And this is on the right is the apparatus mounted on the volunteer's knee.
The most expensive part of this experiment was actually paying the volunteer.
That's right.
And it cost a bottle of Black Bush, which in those days on my salary was a lot of money. It was a guy called McCoy, Jerry McCoy, and we've been colleagues ever since. But he said he had pain in his knee for a year after this. We couldn't use too much local anaesthetic because that would distort the tissue. So we had to use minimal anaesthetic. And you can see then on the diagrams here, we, under X-ray control, we guided these with under drill power into the knee. So you can see it's starting off here, just through the skin, about to engage, and then actually engaged in the bone. And this was, to do it today, it just wouldn't be possible. You wouldn't be allowed to do it. But those were different days. And we got beautiful signals. So it just proved that it was rigid body motion. It was rigid body motion. The other interesting thing was then that I thought the gaps were because the knee just stopped moving, because obviously all these signals we're getting were discontinuous. And I persuaded the department to buy an RVDT, which again was very expensive, but we got it. And I'm sure you've all seen an RVD but those things are still used, are they, in measurement? Rotary variable differential transducer, is that what it was? Transformer. And it was beautiful. So you can see here that when it goes horizontal, the knee had stopped moving. So then I persuaded John to help me build something from what was called a continuous passive motion machine. So you can see here the RVDT is built into it. So John and I made considerable changes to this machine, and you can see we got beautiful continuous signal. So the pair of us had great fun doing this work, and then I moved into clinical practice and developed an interest in hip replacement. And beginning in 1991, we set up a hip factory in Musgrave Park Hospital, and we literally made 4,500 hips, and these were all made the day before surgery. So at that time, probably still today, but that time it was by far the biggest custom implant system in the world. There was nowhere else to do in that volume. So these are the blanks. You ended up with something like this, and these were all made the day before surgery. And we made 4,500, and they all fitted. Apart from, I'm not sure if you know about a big part of John's work was cement, and of course you have to have what's called a cement mantle. And if you look at that femur there on the left hand, so the canal there is about 11 mils in diameter. And another person who I met in 1984 was a guy called Graham Isaac, who was an engineer who ended up working for Charles F. Thackeray, who were making these things. And the first one, instead of being made in Belfast, was made in Leeds, and he brought it across in his bag in a sterile box. And he asked me how thick the cement should be. And we were usually talking about 3 mils of cement to put this down onto it. So I had opened up the operation and opened up the hip. Everything was prepared, and I said, "Well, open the stem." So I opened the stem, and I got something that was considerably smaller than the pen. And you can see here, where's that one I had there? It's away. Okay. Well, it's not the size of a pen, as you can see. And I looked at Graham and said, "I can't put this in." He said, "Well, this is what you asked for." I said, "I didn't ask for that." He said, "You did. You asked for a cement mantle of 3 mils. 11 minus 6 is 5. So I just was in stunned silence, and he said, "We brought 2. So we had a second one. Anyway, so that was the first. So the first one did fit because he brought 2. Where am I? Here we are. So with the number of aims then to restore normal biomechanics, leg length, pressurization of cement, improve component alignment, even cement mantle, and increase proximal support. And we're able to, over a period of years and various publications, to prove all these. Let's let John say a few words then about pressurization.
Well, pressurization was something that we aimed for. The word cement does not imply that orthopedic bone cement is an adhesive. It is not. It fills the gap and transmits load under compression and perhaps shear from the component to the bone. So you need the cement to be right into all the little interstices particularly of the bone surface. And there's various ways of pressurizing cement, but the aim of the custom stem was to trap the cement and to self-pressurize the cement by the insertion of the stem. We produced a laboratory model with pressure transducers around it and started to look at the pressures. We discovered that the distal pressures, the ones at the lower end of the stem, could be up to 6 times the ones at the proximal or the upper end of the stem. That's provided you took some steps to block off the canal within the bone, otherwise the cement would just disappear. And the decay pressure, which was really the longer term pressure at the time when the cement was setting, it's a thermoset material, was the distal pressure was up to twice the proximal pressure. And these are summarising the results. The Belfast custom columns being the ones in the middle, and the high pressures on the left, the red, and of course the blue on the right, are showing you the proximal and the distal decay pressures of the cements. We discovered in the laboratory model that we could produce enormous pressures. Pressures large enough that we were nearly worried about splitting the bone due to internal pressure. But then, of course, we realised that the sort of force we were using to put the stem in was far more than any surgeon could, first of all, exert, but more importantly, maintain while he was holding the stem in the cement and allowing the cement to cure. So we had to turn around and actually measure the surgeons then, but we had to find out what sort of forces they could exert, and that then allowed us to produce a more sophisticated machine, which allowed us to put the stem in at a representative rate, but yet never exceed what would be a reasonable force from the surgeon who was manually putting them in. But they were very effective at producing. That was one of as David summarised, one of the key aims of the stems was to control the cement layers that were being used at that time.
Limb length. So I'm not sure if any. I'm sure some of. So I'm sure all of you have some member of your family who's had their hip replaced. And one of the problems in hip replacement is making your leg the right length. And we're all in this room able to detect very small differences. So limb length is a major issue, and from the very early stages that was one of my obsessions. And when you're doing surgery, all you see is a very tiny bit up here. You know, this is the femur, but you see this tiny bit. And that's a fairly big person in this room, and that's a fairly little person in this room. But they look the same, because all you see is this very small part up at the top here. And therefore, as surgeons, we tend often in very small bones to make the neck cut too high. And simply, if your neck cut's too high, your leg's too long. You know, so it is conceptually quite simple. So these hips were made. So the offset is the distance from the middle of the canal over to the centre of the ball of the head. That's the offset. And we didn't have to worry about that for the customs, because these were all made to fit. So all we had to do was control the depth. And you can see down here, maybe caliper there. So this caliper, as you can see, is what you see down here. So it was very quick and simple to ensure that the depth of the custom component was correct for that leg. So the custom stem was really successful at restoring both the offset, that's the distance from the centre of the canal over to the centre of the head, and also limb length. And there was no arithmetic. All you had to do was to remember the number. So it was 52, so it was quite easy to do. So by 2005, though, the custom hips were becoming more and more expensive to do. And although they did very well, they weren't better than off the shelf. So we then had to move to off the shelf. As you can see then, that the height is no longer enough. But as you can see, as the offset increases, that measurement also increases or decreases if your offset is smaller. So we had to then also measure offset. So we then changed this device. Let's try our new machine here. Is that it?
That's it. That's you. You're going.
That's right. Yeah. So you can see here that this is measuring offset. Is that? Are you able to see that? Yeah. And then you turn it around then, and that there measures your height. So actually, really, Quite simple to do. That was the height measurement, and you then measured head diameter, and you then simply had to subtract the radius of the prosthetic head from the radius of the native head, and this at the time was called mathematics. Now some of you may call this arithmetic, but in terms of international acceptance, this was the death knell of the caliper because of complex mathematics. Surgeons do not like doing sums, especially during surgery, and this, was very simple. It was designed based on my eldest son's mechano toys, and so it's been used, I think, in almost every continent, but only by very small numbers of surgeons.
Pass that round.
Yeah, absolutely. Yeah. So it required arithmetic, and really then over the next couple of decades, we tried to make a new system that wouldn't have arithmetic. Also, destroyed heads are a big issue. So this is a lovely hip to do. So you can see that the head there is perfectly spherical. There's no joint space, so the hip is worn out, and this, what you see there, is actually very painful. But as you can see, the head is perfectly round. Now John will tell me that, of course, that femoral heads are not fully spherical, but as far as a surgeon is concerned, they are spherical.
Right.
So this is a destroyed head, and you can actually see the head there, and it doesn't look very spherical, does it? So again, that was a challenge for our system at that time, because that caliper I've just shown you had to reference off the edge of the head, which if it's destroyed, it makes it hard to do. But this actually ended up being a big asset to us, because if you look at a side view of this same head, that bit's still normal. So this bit of gunge here you see in the middle, there's one part of that is completely normal, and that's the posterior aspect. So this led us then into a whole new area of work. Basically the ring and the IM rod. The ring was to find femoral head center, and the rod was to fix the control, to fix the coronal plane. So I came to John and said, John, could you make something like this? And
well, I didn't need to, because in the armoury of engineering fitters, some of them have a thing called a centre finder.
You can show it in this here now.
Well, I'll pass it around. It's pretty self-explanatory. It's essentially a centre punch inside a cone. And if you want to mark the centre of a piece of steel bar, say to go into a lathe or to whatever, if you place this actually on the end of the bar, give it a tap of the hammer, it gives you a centre punch on the centre. So in other words, the internal geometry of the cone finds the centre, and it would do the same thing on a hip joint. But we needed something slightly more sophisticated, and so the prototype is what David has in the slide, and is a device that does just that. It's a tripod with a reference ring which locates in this posterior, remember, area, which is spherical, David? Yep. Close to spherical, and you can then run a drill through here, and it is locating your best measurement of the centre of the femoral head. Now this was never going to be used in theatre, of course. It's made of brass, but it proved the principle on innumerable foam models like these.
Mm-hmm. Yeah,
I'll pass those around.
Yeah,
sure.
But this is what we used. This is it. We still have it, and you made this in your.
Carry on. I'll pass it around.
But the other thing just to say is that obviously, that's femoral head center, but that's also femoral head center. So that's where the key thing is the coronal plane, and that's where we had to have the rod
to reduce your degrees of freedom.
Yes.
Thank you.
That's yes. Thank you for the engineering correction. Yep.
It's not a correction, David. It was an observation.
So we started to build, and these models you're going to see now happened over many years. So this was one here, and then another one, and you can see here the things to allow. So these were neck resection guides. So your neck cut would be in the perfect location, and a little thing to fit onto the brooch that prepared the femur. This was our most complicated one. This was wonderful. Of course, we used this in the lab in Queen's. It cost many thousands of pounds to make. But as you can see, it probably isn't very practical to use during surgery. And although I would have probably used it, I don't think any of my colleagues would have used it. So I kept getting these turned down. No one seemed to be interested in helping me to take this further. So I began to make it a bit more simple. So you hear that this is more simple. And this then was what I really liked. This is really quite sophisticated. There's still an IM rod, but it was still too complicated. And finally so after over 30 years, we ended up with what we call the Q-ring. And John will now show you this here. So basically, it fits onto the back of the femoral head. And it simply turns over for left and right. And the coronal plane, so we get rid of the IM rod, because if you put it down right onto the neck, the error with that is actually very, very small. So the teaching for the surgeon is put it down on the neck and then lift slightly. So we get coronal plane and femoral head center in one go. So this is even more simple than the caliper, and there are no moving parts, and it just flips over for left and right. So no pins, no arithmetic, no IM rod, reusable, and for me the key thing was free to the end user. One of the big obstacles was getting one of the firms to make these. You can't use them in theatre unless they're made and CE marked, and that's a very involved process. I mean, it takes years. And of course they weren't keen in doing it. I mean, they wanted to make it disposable, so I guess. But I was adamant that this had to be reusable. So these can all go through the autoclave, and it became part of what we called reality-based navigation. So now in surgery, the robot is becoming the big thing, but lots of countries can't afford robots. So this is very simple reality-based navigation. And again, as I said earlier, the level of neck cut, and those of you who have that very small femur up there, you can see how your neck cut will be very different using the Q-ring than it would be in the very big one, and it makes your neck cut in the right place for that patient. So a very simple way of controlling limb length. So that's limb length. The other big thing then is cup inclination, and we invested 2 PhDs and 15 years of research. And inclination really is if you imagine a patient lying on the table on their side, it's the angle of the cup. And for various reasons it's very important, but for various other reasons it's very hard to control. And we ended up with this device here, and I'll just show it to you here. So essentially, one of the things is then that all the companies made what was called mechanical alignment devices, and they were all designed to create an angle of 45 degrees. But we now know that 45 degrees is wrong, and it should be 35. So we simply got round that by putting a 10-degree kink in the rod. So this slides into that there. There's a little ball, and so all surgeons love this, There's
it's a party game.
So all you have to do is to hold it so that the ball is in the centre. And if you're within the centre, you're within 2.5 degrees of your target. So this again now is widely used around Europe. Not yet outside Europe, but I'm sure that will happen. So we can pass that one around. So this is the device here that I've just shown you. So you see, so it really is very simple. But John and I spent, if you looked at all the things that we did, remember we'd one young engineer who started, and I'd explained to her what we were going to do, and she said, basically you're saying that we have to make it some system that allows you to get 40 degrees of inclination on the X-ray. And I said, yeah, that's it in a nutshell. I said, well, what will I do when I've done that? And that was the first PhD. There were several theses since then, so it is surprisingly complicated. But one of the big issues is the position of the pelvis, because when the patient's lying on their side, you have to be lying exactly on your side. If you're rolling forward a wee bit, or your pelvis is tilted down, it's not square. And then even though then you're putting it in at 35 degrees, it will not be the correct angle on the X-ray. So a big challenge for us then was how we kept the pelvis straight. And one of the things we started to do then was to use a little device where we use this simple device to make marks. There are little bumps on the back of the pelvis called the posterior superior iliac spines, and they're very easy to palpate. And as you know, people now tend to be heavier than they were a few decades ago. But most people, like me, when they're heavy, it's more at the front than the back. So the back is easier to get at. And we made this device. This is the Belfast sagittal plane positioner. And the patient lies within this. And you can see then that this back prop here is H-shaped. And that allows us to do this here. And again, this is called a patient orientation device, or POD. This bit here is one that's used during surgery. For some reason, I've left this one on my desk. But the one you see here has got 2 spirit levels. So if a patient's head needs to go down, or they roll forward, so it's in 2 directions, and you simply make sure that the pelvis is square when you start. As I say, there was a huge amount of research went into this as to how hard you'd have to push on this, and this was our proof of concept. So I'll pass again back to.
Well, there's very little to say about this, but you can hold the slide changer, David.
Okay.
This was really an analogue patient who could be rotated to all sorts of different angles and had a compliant surface to account for sort of contact errors with the orientation device. In fact, this was designed by myself and Janet Hill, who's sitting at the back there. We designed it in the cafe in Hillmount Garden Centre one morning while drinking coffee. So this was made and used for some time for, again, assessing use of the instruments, but also some of your colleagues as well in their handling of this new technology.
Yes, so what we showed was that with this because obviously you can imagine when you're doing something soft, I mean you're pushing into something, you can do that there, but with a little bit of experience you learn to put on enough pressure on both to get it equalised, and certainly we were able to show that with a very soft cushion like this here, surgeons were able to pick up less than 5 degrees. And so that was the margin that we were looking at errors of 30 degrees, so getting within a 5 degree thing was a big attraction for us. The problem is then that if you spend all this time setting a patient up, as you can imagine, I know at least one of you has seen an operation done. It's not that delicate. There's a fair bit of pulling and shoving goes on. So you may spend 10 minutes getting the patient perfect, but if they move during surgery, then your measurements are out. So what this device, you can see that this is a sterile one. So this simply goes onto the pelvis on that H-shaped bit and allows you to check just before you put the cup in, that the pelvis hadn't moved. And there's, today all the tables are electric, so your anaesthetist just rolls back towards you until your spirit level. So very, again, reality-based navigation. So very simple and cheap to buy. Here's just some of the publications that John and I have done over the years. These have continued after John's retirement with his colleagues that have come after him. So finally, to come to the conclusion, this is a little picture, World Biomaterials Conference in 2004. There are some very famous people in this picture, and this is Janet, and Janet joined the Orthopaedic Research Unit in November 2008. So this is my office, and Janet maybe tidied up before this picture was taken, so it is very tidy. As you can see, John and I are both holding the femurs that you have here. And as you see, a femur is two ends. So it's got a top end, which is the hip, and a bottom end, which is the knee. And you can see, in fact, in the foreground then, there are two knees. So half my career has been the hip, and the other half has been the knee. So they're both very interesting joints. So hopefully there is no conclusion.
Well, I suppose that's an interesting question. Do you think that the introduction of ethics is reducing perhaps some innovation in a little way?
Look at the surgeon, not me.
Yeah, I suppose I should, yeah. It's very difficult. I mean, I think that my comment, as I often say, is that when I began, research was an amateur sport. You know, it's professional now. Yeah. So what we do is much more controlled, but it does take longer. I mean, those instruments, I mean, I spend a lot of my time working with young engineers, and I always tell them the story. We were I was working in England in 1988, and we were working with a new knee replacement, and it was the unit that Sir John, anybody heard of John Charnley? He's the guy who invented the hip. So it was his lab, and Frank was still there. So Frank was John Charnley's machinist. So Frank used to make the implants that Sir John Charnley put in. And we went to Frank on a Thursday because we found we needed some new instruments to do the knee. And Frank said he was far too busy, and we couldn't have them until the following Tuesday. So I mean, if you go to a young engineer now and you want something made, you're talking about years. If you want a new implant made, you're talking about more than a decade.
Big difference. Okay, open up the questions.
John.
Thanks very much, really good, really interesting talk. So I'm wondering about the custom hips. I know you said they got very expensive, but I guess one of the problems is as well, maybe we don't know what shape to make them, because we can't do CTs now. CTs were going then back in them days, but do you think stuff like 3D printing of metals or even of polymers is going to make that cheaper? And is the problem going to be that we don't actually know what shape to make them?
Yeah. The simple answer to your question is yes. So I talked there, for example, about height and offset in the femur. What we don't talk about is the AP placement of head center. So if you remember, so what I was showing you were 2D images. So the height and offset is simply where head center is, but also head center is in the image as well. And there's a team in Lyon who just published work showing that AP placement varies by 18 mils. And some of you will know a guy called Murray who played some tennis, and he had his hip done, and he had a resurfacing hip done. If you're resurfacing hip, you have no option to put things back where they were, because you literally just resurface the head. So there's no bit goes down into the canal. All you do is the scrape bits off the head and you put a round sphere onto it again. So you're immediately restoring your height offset and the AP placement. And there's debate now as to, so there's a guy called Justin Cobb who works in Imperial College in London, and he's shown quite clearly that resurfacing hips function better than total hips. And it's almost certainly because, I think it's because of Restoration Paramedic Centre, whereas Justin Cobb thinks it's because the femur is still intact. So the whole question is about whether we should be looking again at resurfacing. And I'm sure some of you have heard of the metal and metal disease that we have with hips, and that really destroyed that whole technology. But now Justin Cobb has developed a ceramic on ceramic resurfacing, for which he's now done several hundred, and they're being followed so it's not been released to the market yet, but they are doing very well. So we're now involved in work. So if you remember, I said there was one I made there, the last one I thought was quite nice with the IM rod still. So I've now devised a more simple one that we can actually use the IM rod and measure AP placement during surgery. So we're now in a project to develop that to use in theatre. So what we want to do is to be able to measure it during surgery. But then what we need to do then is to take patients where the AP placement's not good and compare them to patients whose placement happens to be perfect, and see if they compare with the ones that are resurfacing done. And then of course, if it does matter, then the question is how we restore that as well. That answers your question, because at the moment we don't know if putting the head back perfectly AP makes a big difference. I think it does. So I think 10 years from now, a big focus in research will be restoration of that AP bit.
Yes, Justine.
Thank you very much, Professors. That was so interesting to hear. I'm just wondering, do you think that there's anything that we could be doing now to foster the relationship that you are and have demonstrated to us that we could be doing to have something similar and to have, the same great outcomes as you have? But what I can see is that you have a speed from research to commercialization, so that realization and commercialization faster than I have ever seen. And is that because of your, you had that such a close link between engineer and surgeon? And I'm just wondering how we could maybe replicate such a relationship. And I suppose I would also ask too, would there be anything in the teaching, of the engineering or bioengineering or even in the research that you would like to see happening that maybe is not happening? There's, I suppose, two parts to that, to my question.
Perhaps you could allude on how the relationship began.
Our relationship began really, I suppose, just through a kind of a personal relationship, and what developed into a friendship as well as a professional collaboration. And in my experience, Jonathan mentioned that I'd done some work on dental materials, and again, the colleague that I worked for decades with on dental materials with, it was initially just through a mutual sort of empathy, and we started working together and found that we could make progress. And so it was very much, it wasn't organised, it was interdepartmental, interdisciplinary research in Queen's, which was quite difficult actually, because there was no formal encouragement really to do that. I even had engineers, tugging at me metaphorically, saying, "John, just stay within the engineering field, don't go out there." And so those, in my experience, those relationships really, and as David said, it was based on enthusiasm and excitement and satisfaction whenever you got results and when things worked well. So I think you need to look for those sort of relationships, but they're not impossible to find because there's pressures on everybody now to conduct research, and more so than in those days. In my day, when I became an academic, some people in the department did research and others didn't, and that's just the way it was. I don't think that describes the present day. Your second point, sorry, about...
It was just about the teaching thing.
Yes, the teaching thing. I don't know if it still happens in Queen's, but when I was there, we did get surgeons along to talk to our particularly master's students, and find that the surgeons really quite enjoyed getting into an engineering environment, and it wasn't too hard to encourage surgeons first of all to come along and indeed to visit again. So I think in my experience that was an opportunity of being able to forge those clinical links by inviting someone along to talk about what they do. They enjoy talking to the students, and that sort of self-perpetuated.
Thank you very much.
I suppose our big advantage was that we were geographically in the same building, John.
That's correct. Yeah.
So obviously, that this building is down here, and hospitals are somewhere else. And I think we as institutions have to create the mix. It has to be done.
Yes.
It just doesn't happen. And I'm sure a lot of the young engineers I work with are totally fed up because they get. I'm on email contact with them several times most days, but very few of them actually have access to surgeons like that. So I keep telling them that they don't appreciate how good it is, even though they feel they're being overused. So it's how you bring people together, and that requires effort on both sides. And of course, a lot of what we heard this morning, of course, is different to what we were doing. It's at a molecular level. I was just saying earlier on today. The biggest problem today in arthroplasty is infection. That's our biggest problem, and finding some way of preventing or reducing the infection. That's the big issue, because everything else is improving.
Thank you so much.
I think that is a point. The privilege of looking back on it, of working in the same building. My boss and colleague Jimmy James, who I introduced a little bit earlier, he was a consultant orthopaedic surgeon. I was a relatively newly graduated engineer. We didn't only work from the same office, we shared the same desk. If one of us was sitting down, the other one couldn't. And that never ever led to any difficulties or any arguments or any competition. But we sort of just mixed and matched. And we weren't talking about research all the time, and we were doing various things, but just living in the same environment made a huge difference. Certainly got me inducted into the fields and looking for opportunities. So
Thank you so much.
I want to throw this.
Go on. Yeah. Any further questions? Okay, in the interest of time, I'll thank the keynotes again.